Science fiction delights in showing us humanity's future on strange new worlds we will find out among the stars. But it is very likely our future will be on massive artificial worlds and megastructures of our own creation.
So welcome to Science and Futurism with Isaac Arthur, and I am the aforementioned host, Isaac Arthur. Just under 8 years ago, the channel began with an episode cataloging a number of what we call megastructures, huge artificial constructs that in many cases would rival entire planets in size and serve a similar role as our future homes. Back in the day, the graphics on the show weren't terribly impressive. Indeed, most megastructural visuals in existence were made after that episode, many for this show, and the audio was terrible. It was the first episode of the show, and the only one not to include the episode transcript in as captions because there wasn't one. As time went on, our audio and graphics improved, and I got some speech therapy for my speech impediment. And folks often ask why I've never redone that episode, when almost every other early episode has gotten a redo, or reboot, or even an entire extended series. Indeed, we gave many megastructures their own episode in our megastructural series, but it did indeed seem time to catalog all of them again in a summary form, including many new ones we and others have dreamed up since then. Needless to say, even keeping it quick, this one is going to be a long episode, easily beating out our previous record holder, the Fermi Paradox Compendium, which was over 70 minutes. So get yourself a drink and a snack, or even two, and let's get started. Also, in the interest of preserving my vocal cords, my wife and livestream co-host, Sarah Fowler Arthur, will be alternating narration with me between entries. Now, obviously, even giving ourselves an extended length episode is not going to give us much time to get into details, but we try to approach this categorically, and that's rather tricky because a megastructure pretty much means anything artificial and enormous, but the majority of them are artificial habitats designed around terrestrial ecology and humans. Some exist for maximum efficiency and practicality, things we might build in a century or two, like the O'Neill Cylinder or Stanford Torus. Others for the sheer ridiculousness of them, what we call a BWC or because we can megastructure, like flat planets or cube-shaped ones. Some rely on concepts that need explaining, like spin gravity, and will apply to several structures. In the end though, the determining factor for format is just that I know I'll think of ones I forgot while I'm writing, so we're going to do them alphabetically, and those concepts relevant to megastructures that aren't megastructures themselves, like spin gravity or grav plating, will get their own entries and we'll just reference the concept in the megastructures. With that in mind, let's begin our list with one of the most important engineering tricks for mega engineering, active support. Then we'll look at a megastructure needing it, one of the most impressive megastructures out there, the Alderson Disc.
Active support. Active support is a method that can be employed to build structures that no known material could support via compressive strength. While it comes in many forms, the most conceptually simple way of thinking of it is as a hose when you've turned the water on and grows stiff as that water flows into it. For objects like a Lofstrom Loop or orbital ring, it is assumed that it will be high-speed metals moving inside magnetic confinement, accelerated by applying electromagnetic shoves, and contained inside a stationary sheath. In high-tech megastructures, this may be a magnetically shielded structural support with warm-temperature superconductors inside it, limiting the need to apply additional power to keep the active support intact and rigid. These objects can be arbitrarily strong and large. Most common shapes would include a circle or ellipse, such as an orbital ring, or a straight line, such as an Atlas pillar or space tower. They form the foundation of many megastructures. See also Atlas pillar, Lofstrom Loop, Orbital Ring, Shellworld, and Space Tower.
Alderson Disc. The Alderson Disc is an immense flat planet built with the top and bottom sides you could live on, around a star at the center of the disc. It was first suggested by Dan Alderson, a scientist at the Jet Propulsion Laboratory who was active in sci-fi circles and talking with sci-fi writers, particularly with Larry Niven, who wrote about so many megastructures. In simple form, an Alderson disk around our own sun would be a flat plate with a hole in the middle, stretching from as close as you could get to the sun, right out to the distant, frozen depths of space, and of such immense mass that it would dwarf the star at its center. The default Alderson Disc masses roughly 3,000 solar masses, a billion Earths, but could be built around bigger stars or red dwarfs, or entirely artificial suns. The critical problem with building an Alderson Disc are twofold. First, it takes immense strength to keep the disc from collapsing either downward into a flatter plate or inward into a sphere. Second, most of the sunlight is completely wasted, going above or below the disc, and what light does come in arrives from the side. This places the entire disc, top and bottom side, in perpetual twilight, growing dimmer as the distance and air interfere. This results in a warm center and frigid outer layers, virtually none of which are livable. Some suggest addressing this by bobbing the star up and down in the center, so it rises above and below, and this is technically possible since the star is the smaller object and could be placed on an ultra-eccentric orbital path through that central hole. However, there is no plausible natural path that would produce anything like a 24-hour day, and such an orbit would require constant stabilizing efforts. For all these reasons, an Alderson Disc is often considered an example of a BWC megastructure. To address the first problem, the disk collapsing, in the absence of arbitrarily strong materials, we make use of countless orbital rings, each a circle just a bit wider than the last, each having an angular momentum appropriate to the orbit at that distance. Keep in mind that the star's own mass is soon dwarfed by the inner rings of the disk. We then place a sheath above and below these nested rings to create the disk and keep them separated by using Atlas pillars to keep the top and bottom from crunching down on each other or the orbital rings below. Care must be taken to include segment walls to prevent all the air, water, and even land from rushing to the center. These segment walls may be disguised as mountain ranges. Large subterranean pumps may move air and water back to the places they need to be to assist in this. Additionally, by varying the mass and density of the rings to increase their own gravity, we may cancel out some of that central pull, keeping gravity pointing straight down throughout the disk. To provide power for all the active support, the inner ring inside the plate nearest the star may be a solar power collector. To permit a 24-hour day or seasons, we may place large statite or lagite solar mirrors and shades above and below the north and south pole of the star, at distances comparable to the disk's radius, to reflect sunlight back down onto the planet. The wide statite disks may include wedges of reflective material and shades, or simply have tilted reflective bands, to cause the sun to reflect down on places for the chosen time period and strength, and thus replicate a day-night and seasonal cycle. While this structure is popular in science fiction, it would generally be one we would deem physically possible, but not a practical approach to building living area. However, it does have the advantage of being one of the largest structures you can make that allows a continuous Earth-like living area, so long as you include polar statites, being bigger than even a classic Dyson Sphere, though smaller than a Birch Planet. See our episodes Megastructure 6, Discworlds, or Megastructures Flat Earths for more details. See also Active Support, Discworld, Lagite, Orbital Ring, and Statite.
Arcology Megatower. Arcology megatowers are envisioned to be very tall and wide buildings which are ecologically self-contained in whole or in part. This is typically assumed to mean towers dwarfing any modern skyscraper, and including not only their own internal power sources and water and air processing, but also food production. In science fiction, these are usually seen in the dystopian settings of trash-strewn and graffiti-covered steel and concrete jungles, but these might range from utopian to dystopian, big or small, and given their scope would be more likely to be an equivalent to a gated community than a slum. A space outpost with all of its own internal life support in tower form would most likely be the first true total arcology, though it can also come in underground form, as it need not be specifically tall, and it could be wide or underground. The term arcology, being a combination of the words architecture and ecology, was originally meant to simply encompass any group of structures built to be ecological and self-sufficient. The giant skyscraper concept comes later, but it is better known, and thus we distinguish it formally by calling these an Arcology Megatower. See our episodes Arcologies and Arcology Design for more details.
Arkship. An Arkship, conceptually based on the idea of Noah's Ark, is meant to be an interstellar spaceship able to carry humans and terrestrial biology to another world. This is usually in the form of a giant cylinder habitat with a spaceship drive and towns, gardens, farms, zoos, and nature habitats inside that habitation drum, able to live there via artificial lighting and power until the ship arrives at the colony planet. Generally speaking, the immense amount of energy needed for artificial lighting and life support, even for many centuries, is still tinier than the amount of energy needed to get the ship moving at interstellar speeds or to slow it down on arrival. These are also often known as generation ships. A second style Arkship, one containing frozen or digital samples of life forms, would generally be smaller and not qualify as a megastructure, and we often call this style a seed ship. See our generation ships and interstellar colonization series for more information.
Artificial sun. Artificial suns and stars come in many forms. This could be an entirely normal star simply made by people, or one using normal stellar processes but made from an atypical material, like pure deuterium, to allow a smaller size, or could be ones with a star-lifting apparatus to remove helium and heavier elements to extend life and allow refueling. This can also include non-fusion options like black holes, producing power by pouring matter into them or by hawking radiation. Often in the context of megastructures, though, it represents the artificial lighting in the habitat to produce sunlight for the ecology. This may include traditional electric lighting or mirrors, bringing lighting in from an external source. This may orbit an unlit rogue planet to produce a geocentric world, or it may be vast pillars in the form of sun towers rising above the landscape. See our episode Making Suns for more details.
Asteroid Colonies. Asteroid colonies are more of a location for megastructures than a megastructure themselves, but given that such minor worlds outnumber traditional planets several thousand to one, they are likely to be one of the most common settings for them. The most likely megastructures in one would be a cylinder habitat built inside mined-out areas, or next to it and enclosed in the mining spoil till it merged. The asteroid offers protection from space debris and attacks, and possibly concealment. One special note, it is often suggested you could carve out an asteroid and spin it to live on the interior with spin gravity. In practice, your typical asteroid is a loosely bound ball of gravel and should not be spun at any rate. Instead, you would hollow it out, put a thin shell inside to buttress it, then place the cylinder habitat inside that, rotating around on its own. Larger asteroids might contain hundreds of individual cylinder habitats chained together, or later be turned into thin outer shells, full of networks of cylinder habitats such as Buckyhabs. Such hollow shells would likely be far wider than the original asteroid. See also Buckyhabs' cylinder habitats.
Atlas Pillars. Named for the Titan Atlas from Greek mythology who held up the sky itself, the Atlas Pillar is a type of active support structure able to hold up the sky or repeating layer of land above it. Typically envisioned inside Matrioshka Shellworlds, where concentric shells covered in land and sea and artificially lit allow us to maximize the use of mass for generating gravity and using as living area. Atlas pillars could potentially be made of some type of unobtainium that was vastly strong in compressive strength, but would most likely have an interior track in which magnetically accelerated materials ran. If technology permits, this may be magnetically shielded superconducting tracks, requiring little to no additional coolant or power input. Alternatively, they might be built of very temperature-resistant materials and the waste energy used to heat or even light the lower layers of many layered habitats. Strong ones may also hold artificial lighting or even additional shelves of habitats running up the Atlas pillar, like leaves on a tree. They might also have spirals around their outside to allow walking directly between layers of a habitat. See Active Support and Matrioshka Shellworld.
Banks Orbital. A Banks orbital is an enormous ring habitat unique for its natural day length. Named for science fiction author Ian M. Banks, who first described one in his novel Consider Phoebus, where they also have the nickname of God's Bracelet. A Banks orbital has all the normal features of a ring or cylinder habitat, but varies in 3 ways. First, the required tensile strength vastly exceeds any known material. Second, it is large enough that it can have rim walls holding the air that are shorter than its width or radius, allowing an open air habitat. so you can fly your spaceship straight into the atmosphere and land inside the ring, like on a planet but unlike a typical closed habitat. Third, there is a unique radius and spin rate for any combination of day length and desired gravity. A Banks orbital rotates once per day, and its orbit around a star is slightly cocked at an angle to allow the sun to shine on the inside of its far side, creating a day of normal length and characteristics, including sunrise and twilight. Seasons can also be emulated by tilting the ring more. The width of a Banks orbital is arbitrary, but given that the purpose is to use the natural day, the ring's band width is expected to be considerably skinnier than the ring's diameter. For an Earth-simulating diameter, every 48 kilometers or 30 miles of width to the band represents an additional Earth's worth of surface area for the habitat. In the case of Earth gravity and day length, this is 1,843,509 kilometers radius, or 1.15 million miles. This is the size typically under discussion, but for cases where one would need to distinguish, we might call this a Terran Banks orbital, while one seeking to emulate Martian gravity and day length would be a Martian Banks orbital, roughly 700,000 kilometers in radius. You might also have a Venusian or lunar Banks orbital. The radius of such an orbital is proportional to the desired gravity, or the square of the desired day length. Thus, a Venusian or lunar Banks orbital would need to be far larger as their days are much longer than Earth's.
The Bernal Sphere. The Bernal Sphere is one of the oldest megastructure concepts, having been proposed by John Desmond Bernal in 1929, and is a hollow rotating spherical shell. They can be of any size the material's tensile strength can permit, but the original design was 5 miles or 8 kilometers in radius. This gives it 314 square miles, or 803 square kilometers, of interior surface people could live on, and he estimated 20 to 30,000. This is essentially a pressurized sphere where spin is producing the gravity, and thus will be the highest at the equator and non-existent at the poles. Gerard K. O'Neill, known for the O'Neill cylinder, also known as Island 3, had 250-meter radius and 900-meter radius versions of the Bernal Sphere as Island 1 and 2. The Bernal Sphere would likely make use of ring-shaped tiers inside the sphere running as bands, with the widest at the equator to keep the land flatter inside. See also O'Neill's cylinder and spin gravity.
Birch Planet. Paul Birch, who detailed such concepts as the orbital ring for active support, suggested they could be used for building massive hollow shells we might fill with matter to make artificial planets from, what on this channel we call Shellworlds, and he suggested these might even be built around giant black holes, such as we find at the center of many galaxies. While those built around normal black holes fall into our category of mega-Earths, those built around these truly enormous galactic core black holes we call a Birch Planet in his honor. The one in the center of our own galaxy is estimated at roughly 4 million solar masses, or 1.3 trillion Earth masses, and thus a single-layer shell around such a world, emulating Earth's own gravity, would have 1.3 trillion times the surface area and living area that Earth does. This is considered the smaller end of Birch planets, as they may have many layers. One with 750 such layers would have 1 quadrillion Earths worth of living area. They may also be built around bigger black holes. You can feed nearly 1 trillion solar masses, or an entire galaxy, into a black hole before its event horizon would extend out beyond where its gravity was equal in force to Earth's surface, and thus would be the maximum limit to any Birch planet seeking to emulate Earth's conditions and built outside a black hole's event horizon. As tidal forces near that black hole are minimal, we cannot rule out attempts to build down inside that horizon either, effectively removing them from our universe. Though in practice, frame dragging would likely prevent building a Birch planet to quite this size, a maximum-sized Birch planet contains an entire galaxy or even multiple and may have thousands of layers, potentially reaching over 1 sextillion, or a billion Earths worth of living area. It is one of the few megastructures best measured by how long it takes light to traverse it, as larger ones can measure a light year wide. The Birch Planet is the largest known megastructure allowed under known physics in terms of continuous habitable Earth-like living area. Lower levels can have time running significantly slower than on higher levels due to the relativistic distortion near the event horizon. Such habitats are essentially isolated universes in of themselves, as they could consume all or nearly all of the matter in a region that is gravitationally bound, and could be powered for eons by slowly adding in mass to the black hole to generate the power for artificial lighting in the habitat, probably via sun towers. Birch planets have an enormous escape velocity, being easy to reach but hard to leave, and are considered by the channel to be one of the most plausible fates of Earth, or the homeworld of any civilization that would prefer to use automated mining to bring matter home, thus mining the entire galaxy out to expand their homeworld till it became a Birch planet. A multi-layered Birch planet can make the lowest level much thicker and space subsequent layers to achieve self-gravity without the central black hole, and is called a superself. See also Banks Orbiter, Black Hole Gravity Generator, Matrioshka Shellworld, Mega-Earth, or Sun Tower.
Bishop Ring. The Bishop Ring is a spin-gravity continent-class habitat proposed by Forrest Bishop in 1997 to take advantage of the greater tensile strength of materials such as carbon nanotubes and graphene. With a proposed radius of 1,000 kilometers and a width of 500 kilometers, it would be comparable to India in size, at 3 million square kilometers or 1.2 million square miles of internal land and sea. While large enough to be an open-air habitat, even with rim walls and air leakage, it's debatable if any point is served by not having the ring enclosed as a cylinder, with rim walls all the way to the axis or over top to form a torus. Its open-air format is principally an acknowledgement that it is large enough for that to be possible, not necessarily preferable. A Bishop ring 1,000 kilometers in radius would rotate every 33 minutes to produce Earth-like gravity, which might be slow enough for the motion of the stars not to be nauseating during night cycles, but this structure still requires an artificial sun for a normal day, either by use of mirrors or powered lighting. We would anticipate a Bishop ring would have tethers running up to the hub like spokes on a wheel for easier transport, and possibly vacuum trains running on the outer side of the ring, which rotates at 3.1 kilometers per second, a very good speed for releasing spaceships at. Like many larger spin gravity habitats, the speed of the drum may be advantageous for saving fuel for spaceships docking or embarking. Bishop rings would be large enough to serve as a home to 1 billion people, or serve as a nature preserve for even the largest ecologies. See also carbon nanotubes, cylinder habitat, McKendree cylinder, ring habitat.
Black hole gravity generator. Artificially created black holes, or even naturally occurring ones for mega-Earths, can serve as a source of mass for generating gravity for artificial worlds. As a point-like object, it avoids normal problems with material density, thus allowing even modest asteroids to have Earth-like surface gravity, mini-Earths, or create Earth-like gravity on truly enormous worlds such as super-mundane planets or mega-Earths. As with any natural gravity source, the amount of surface area existing at the desired gravity is proportional to mass, thus a black hole 4 times more massive could permit 4 times as much surface area on the globe. Black holes do not eliminate the need for larger amounts of matter to produce gravity, but they do allow less useful and hyperabundant materials like hydrogen and helium to be used, as opposed to carbon or iron, or potentially even dark matter, which makes up the supermajority of mass in the universe. While helium and hydrogen dumped into a black hole cannot be used for fusion, the power generated by dropping matter into a black hole tends to be at least an order of magnitude higher than fusion could produce, thus minimizing their value as a fuel for fusion power. See also Birch Planet, Black Hole Power Generator, Shellworlds, Mini-Earths, Mega-Earths, Super-Mundane Planets.
Black hole power generator. Black holes may generate power in multiple fashions. Small ones typically by hawking radiation, large ones by dropping matter into them and collecting the radiation coming off them from their acceleration or orbital collision in the accretion disk. In all cases, the power produced tends to be a high fraction of the mass energy involved, and thus is considerably more efficient as a power source than even fusion. And other than the creation of the black hole, power collection is relatively low-tech. As such, black holes of various sizes may serve as everything from a power source on a large spaceship or personal space habitat to the superstellar power source of Birch planets and other constructs larger than Dyson Spheres. Because of their very efficient nature, they offer incredible service lifetimes, with a 100 megawatt Hawking generator having a service lifetime of 10 trillion years, and at a mass of 1.9 gigatons, able to generate comfortable gravity to a large personal habitat or building. Alternatively, drip feeding the sun's mass into a black hole to supply power, at perhaps 20% mass to energy conversion, at a rate of 20 megatons per second, would produce the same energy as our sun, but for 3 trillion years, hundreds of times longer than our own sun's currently estimated remaining lifetime. If black holes may be formed, rather than only as the byproducts of supernova, they represent the best power source under known physics and would be expected to be a centerpiece of not only a civilization's power and infrastructure, but its literal center as a source of artificial gravity, too. See our black hole series for more discussions of their uses for world building and ship propulsion, as well as weaponization.
Buckyhab. A bubble habitat is one designed to float by buoyancy in an atmosphere, and is essentially a large blimp, though these may range in size from the size of a modern blimp to being continent-sized. On many worlds, such as Venus, you may have an atmosphere whose main makeup is heavier than air on Earth, thus allowing oxygen and nitrogen to be used as a lifting gas instead of helium or hydrogen. Advanced materials may allow building materials filled with hydrogen that do not leak, or even which are vacuums on the inside, and thus would perpetually float or have a longer useful lifetime comparable to many building materials like wood. Buckyhabs based on biotechnology might be grown instead, either as an equivalent to a buoyant coral reef or tree, or possibly a very large parallel to a whale or blowfish. See our episodes Void Ecology and Space Whales for more discussion of such concepts.
Buckyhabs. Buckyhabs are connections of cylinder habitats to form a buckyball, forming a cage-like structure of 90 identically long cylinder habitats connecting in trios at 60 hubs, forming a soccer ball shape. This number of habs and edges is mostly noteworthy because a buckyball is a carbon-60 atom, very tied in with carbon nanotubes and graphene, in early speculation of supersized habitats. In practice, we would expect people desiring more living space would build larger numbers of cylinder habitats connected together rather than making individual habitats longer or wider than was deemed optimal from experience. One composed of Island 3 O'Neill cylinders would contain 90 such habitats totaling in at 145,000 square kilometers or 90,000 square miles of living area, comparable to Michigan or Minnesota. Alternatively, one composed of McKendree cylinders might be double Earth's available area. As cylinder habitats are likely to often have additional non-rotating sections and other supplementary facilities, as well as benefiting from a non-rotating superstructure, such buckyhab arrangements are ideal for shared ancillary facilities and permit a thick spherical outer skin for protection, heat radiation, and solar power collection. Such polygon arrangements could easily be platonic solids and may have nested layers, a smaller soccer ball inside the large one, connected in between by additional cylinder habitats.
BWC Megastructure. BWC, or Because We Can Megastructures, is a nickname for those types of megastructures which are interesting as concepts but wildly impractical enough that we would only expect them to be built for prestige or tourist value. Though in a system of potentially millions of normal habitats and worlds, such rare oddities might be built economically for their novelty value. Examples include cube-shaped planets and disc-shaped planets, though it should be noted that sometimes they can have specialized values as, for instance, a coin-shaped world allows identical seasons, temperature, and weather at all points, ideal for a beach resort planet, that a spherical planet lacks, with frozen wastes at the poles. Needless to say, what qualifies as a BWC megastructure is somewhat subjective, and many might feel virtually all megastructures fall into this category.
Caplan Thruster. A Caplan Thruster is a method for moving stars proposed by Matthew Caplan in 2019 for using statites to concentrate solar energy and erupt solar wind in a beam out from a star, which would then pass through an enormous Bussard ramjet assembly and jets of oxygen-14 to push a star at a faster rate than a traditional Shakatov thruster would allow. See our episode Fleet of Stars for more discussion of potential methods of moving stars. See also Helios Drive, Nova Drive, Quasar Drive, Shakatov thruster, star lifting, and supernova drive.
Carbon nanotube. Carbon nanotubes, or CNT, are a type of carbon allotrope that, along with buckyballs, represent materials considerably stronger than diamond that, in the 1990s, popularized the idea we might create megastructures relying on super tensile strength materials, such as space elevators and bishop rings and McKendree cylinders. These are materials that are virtually impossible to tear apart, no matter how hard you pull them and how much tension you place them under, and along with graphene became commonly referenced as the foundation material for megastructures. For this reason, they are ubiquitous in discussion of megastructures and many other sci-fi or futurist topics. See also bishop ring, graphene, McKendree cylinder, and space elevator.
Chainworlds. A chainworld is an example of linking several hoop worlds or other torus-shaped habitats into a long chain-link arrangement, potentially wrapping around a star. This has limited utility but would allow airplanes to fly directly between all these interconnected worlds. Airborne seeds or avians might also be able to traverse between the hoops, though overlapping the hoop's atmosphere would be likely to generate powerful perpetual storms at the intersections, while the ground above and below it, so to speak, rotated past.
Chandelier Cities. The concept of a chandelier city in the clouds of gas giants was explored in our episode Colonizing Neptune, and relies on the idea that tensile strength is every bit as reliable as compressive strength, so that hanging buildings down from large orbital rings around a world allows upside-down, chandelier-like cities suspended from the ring. These might be common features on gas giants, ice giants, or thick atmosphere super-Earths, and any other world where living on the surface was not viable, though the technology works on any world, including Earth or airless planetoids.
Clarketech. Clarketech is not a megastructure, but is often a feature of many proposed megastructures, requiring special properties or built to do exceptional tasks, like wormhole networks. The name is derived from Arthur C. Clarke's famous quote that any sufficiently advanced technology is indistinguishable from magic, and is the name for various technologies that folks have suggested that would not seem possible under currently known physics, and can include seemingly impossibly strong materials or other types of unobtainium, as well as faster-than-light systems and perpetual motion machines. See our episodes Clarketech for more discussion of these near-magical technologies. See also unobtainium wormholes.
Cube World. Cube-shaped worlds, a subtype of polyhedral worlds in general, classify as examples of BWC megastructures. Construction would require heavy use of Atlas pillars or other active support, and by default would have their gravity highest at the middle of each of the 6 faces and lowest at the 8 corners, furthest from the center. Gravity would also aim at the center rather than perpendicular to the surface, though strategic variation of density throughout the cube and some rippling in the surface might minimize the discrepancy of down not being in line with your head and feet. As with other flat worlds using normal gravity, there will be a tendency to bulge the air and water toward a spherical shape which can be counteracted with enough effort. Many other shapes, such as dodecahedrons or buckyballs, follow similar rules and limitations as cube worlds. See also active support, Atlas pillars.
Cylinder habitat. Cylinder habitats are expected to be the megastructure type on which the bulk of humanity lives in the future, if humans remain a dominant species and seek to emulate Earth ecologies around them. Cylinder habitats operate on 2 critical principles. First, that gravity can be mimicked by rotation using the same centrifugal force effect that washing machine spin cycles use. Second, that it takes far less mass to build a cylinder or ring habitat than an equal amount of naturally gravitating surface area on a planet. Generally, many hundreds of thousands of times more living area per unit of construction materials, so that a world like Mars might be disassembled to grant us 100,000 Earths worth of living area, not a fraction of Earth's. For a detailed explanation of how spin gravity functions and differs from normal gravity, see our episodes O'Neill's Cylinders and Life on Board an O'Neill Cylinder. As discussed in those episodes, while cylinder habitats are typically portrayed as spinning freely in space, it is most likely to be either part of a large complex of space infrastructure or paired up with a twin cylinder, or several more in a Buckyhab configuration. A cylinder habitat is likely to be inside a slightly wider non-spinning or slow-spinning outer cylinder to provide shielding, or inside an asteroid, or with other facilities inside a superstructure. We expect them to make up the bulk of residential habitats and nature preserves in space, as well as to be common features of any spaceship with humans on board and long travel times, such as an interstellar Arkship. In such cases, we often call the cylinder portion of that ship the habitation drum. You can nest multiple habitation drums inside each other, or give a drum multiple levels. Size of cylinder habitats in terms of diameter is controlled by the available materials in terms of tensile strength, where conventional steel or titanium can allow a cylinder that's several kilometers wide, and graphene might allow one over 1,000 kilometers wide, known as a McKendree cylinder. Unobtainium or active support might be used to craft even wider habitats. There is no maximum length to a cylinder habitat. Very long ones are known as a topopolis. A Kardashev II civilization of humans seeking to maximize O'Neill cylinders around a star would require roughly a quadrillion such cylinder habitats, each home to potentially hundreds of thousands of people. See also Banks orbital, Bishop ring, McKendree cylinder, Ribbon world, ring habitat, ring world, rung world, topopolis, unobtainium. Dark Sky Station. On the smaller side of megastructures, especially in terms of mass, JP Aerospace's Dark Sky Station is an enormous starfish-shaped buoyant platform, potentially kilometers across, that would sit 43 kilometers up in the air and be a midway changeover point between ground to station and station to space traffic. These may see heavy usage on other types of planets with thicker atmospheres. See also Sky Cities.
Disk World. Flat Earths and disk worlds are often classified as BWC Megastructures, but in practice, a disk world rotating like a spinning coin in orbit of a star is not a particularly bad use of mass for gravity compared to a typical shell world. While you get slightly less surface area per unit of mass than a sphere, you do not get an extreme temperature difference between poles and equator. Thus, a disk world might be considered optimal for those seeking to create a uniform climate and ecology. As a BWC megastructure, it is only likely to be built by civilizations that already have so many artificial worlds of more efficient types that such specialized worlds might be probable anyway, such as a world of many shallow seas and snaky coastal islands for a beach resort, or one given over entirely to one specific ecosystem and apex organism, like a planet built principally for preserving, at a large scale, elephants, blue whales, or the Amazon rainforest. Disk worlds have limits on how big they can be and spin on an axis to simulate day and night, and must have non-uniform radial mass distribution to keep gravity pointed down to the ground, not tilted to the center, with air and water to follow. See our Megastructure series episodes Disk Worlds and Flat Earths for more details. See also Active Support, Alderson Disc, Sombrero Planet.
Dyson Sphere. While originally proposed by Freeman Dyson as a swarm of orbiting bodies around a star, the concept has stuck in the popular imagination as a hollow shell around a star that people live inside, where the lit surface is more than 1 billion times that of Earth. In the absence of some sort of artificial gravity, there would be no gravity on the surface of such a shell, and those inside would fall into the sun, followed by the shell itself, unless made of an impossibly strong and rigid material. So too, there is no night time inside such a sphere, which must then be wider than Earth's orbit from the sun to avoid all those inside burning to death from the endless daytime. For this reason, the Dyson Swarm is considered better. However, a Dyson shell is possible with some variations. First, the inside could be a large solar collector, and people could live on the outside with artificial lighting as an example of a mega-Earth, or in this case, a giga-Earth. Second, a ring-shaped slice of Dyson Sphere, made of a super-rigid material, could be spun around the star to produce artificial spin gravity, and this is the concept of a Niven ring world. A collection of many of these rings tilted at different angles can produce a quasi-Dyson shell or ring Dyson. It is also possible to create a very wide ring or a bridged sphere with caps that would have lower gravity at higher latitudes than at the equator, and leave the poles off, in favor of rim walls and possibly having statite solar mirrors or power collectors at the polar regions. This still requires incredibly strong materials beyond anything permitted under known physics, except for the use of active support similar to what we can use to construct a Niven ring world. Such a partial sphere could be made wider if the polar caps reflect sunlight down into the main sphere and result in the same total living area of 2 billion Earths. Day and night shading can be accomplished as with a ring world with an inner ring of sun mirrors and shades.
Dyson Spike. A Dyson Spike is a type of Dyson Sphere where a rigid shell has been placed around a star using unobtainium, but where artificial gravity is not possible, and so the surface is dimpled with billions of cylinder habitats that generate spin gravity inside them. This setup can also work if the shell is a statite principally for power generation, but to which a small portion is given over to living area, such as homes and environments for people living in conjunction with a Dyson beam platform. External spikes also allow better radiative cooling to such a shell. See also Dyson Sphere, Dyson Swarm, Matrioshka Brain, and Dyson beam.
Dyson Swarm. When Freeman Dyson originally envisioned a Dyson sphere, he was discussing a large collection of orbiting bodies in a cloud or swarm around a star, rather than a rigid shell. However, the idea of a hollow shell around a star with people living inside it has been popularized as a Dyson sphere. A Dyson swarm is the term we use to speak to Dyson's original idea rather than the hollow shell. Such a swarm could be composed of any single type of megastructure, but we tend to assume that most Dyson Swarm civilizations, also known as Kardashev II civilizations, would use a large collection of many different types of space stations and structures. In this regard, a Dyson Swarm is considered a megastructure in the same way a city is considered a building, which is to say, Dyson swarms of things composed of many megastructures. It is usually assumed that civilizations will trend towards being Dyson swarms around every star eventually, though in practice, many civilizations may disassemble stars in favor of using them to power fusion reactors or black hole-powered generators. Nonetheless, spherical packing of habitats together into immense swarms or clouds that were outwardly identical to Dyson swarms would still be expected, as it provides for minimal travel times and communication lag. As discussed in the second episode on this channel, the Dyson Dilemma. See our episode Dyson Dilemma 2.0 for details.
Ecumenopolis. A Ecumenopolis is a city which covers an entire planet. This presumably would include dwarf planets, super-Earths, and moons as well. While usually assumed to turn an entire planet into one vast sea of concrete and steel, in practice this is likely to be a world with many vertical levels and vertical farming in play. The main restriction on population is expected to be heat dissipation. See our episodes Ecumenopolis and Can We Have a Trillion People on Earth?
Edersphere. An Edersphere or Eder bubble, named for Danny Eder, is a balloon-like megastructure typically of gas giant size ranges. Unlike most active support supramundane worlds, the Edersphere uses the pressure of gas as it compresses to resist the gravity of that gas pulling on the membrane above it. People live on the surface shell, which can be covered in a thin terrain, allowing a world potentially many hundreds of times larger than Earth in a living area. The shell is likely to be thick steel or other strong metals, not rubber or any other flexible or thin material, as at that scale, almost any material would be flexible enough to act as a membrane. It is likely that such a shell world would still include active support members such as orbital rings or atlas pillars that could be turned on in an emergency, conserving power, or which could work in tandem with a pressurized gas to allow a wider range of artificial worlds than an Eder bubble alone might allow. See also active support, atlas pillar, orbital rings, shell worlds, supramundane worlds.
Fusion candles. A fusion candle is an enormous fusion drive placed in orbit of a gas giant designed to suck hydrogen, deuterium, or even helium out of the atmosphere, run it through a fusion reaction, and use the energy released to send out two superheated rocket jets in opposite directions, up and down. The lower levitates the platform while the higher goes into space to shove the gas giant. By this method, you can move a gas giant to a different location, such that you want to move one closer into a system to warm its moons for terraforming. See our episode Colonizing Jupiter for more discussion.
Graphene. Graphene is a carbon allotrope of immense tensile strength whose discovery opened the door to the serious consideration of building rotating habitat megastructures far larger than O'Neill's cylinders. They have many other useful properties as detailed in our episode The Impact of Graphene.
Grav Plating. Grav Plating is a catch-all term for any technology that can be used in the floor of a spaceship or space station to produce artificial gravity without rotation. It is usually assumed to operate via unknown scientific principles in science fiction settings. In practice, the only known way to produce grav plating under known physics would be to create mini-charged micro-black holes and arrange them inside a floor in a hexagonal pattern. See our episode Moon, Mega City for more discussion of black hole gravity plating.
Hammer Hab. A hammer hab, also called a bolo hab, is a spin gravity habitat where minimal living space is needed, so that the living module itself is suspended from a long tether that is swung in a circle, usually around a larger ship, itself in microgravity. It can also be paired to a twin with no hub, or you may have many such habitat modules or docking spaceships on tether from a central hub resembling a Ferris wheel.
Helios Drive. The Helios Drive is a variation of the Chicago thruster that incorporates star lifting technology to move stars and can accelerate a star faster than the Chicago thruster, but achieves a slower maximum velocity because it uses accelerated plasma as the drive. By turning mirrors toward a star instead of reflecting its light in a single direction like the Chicago thruster does, we can cause a stream of hot matter to come off the star like a rocket flame. This technique works well for moving dangerously large stars which might go supernova out of a region of space, as it takes far less time to get the star moving at interstellar speeds and also reduces the mass of that star, potentially extending its lifetime. A variation of this using Bussard ramjets to fuse the plasma as it comes off the star to provide more thrust is called a Caplan Thruster. See also Caplan Thruster, Chicago Thruster, star lifting, and Stellar.
Hoop World. A hoop world is a donut-shaped planet that classifies as a BWC, because we can, megastructure, and would be expected to have a highly variable gravity over its surface as the matter inside the hoop will pull the most on the outside equator, and least on the inside equator, where the other side of the hoop's gravity pulls in the opposite direction, and at an angle least on the pole lines as the hoop world has no conventional north or south pole. Storms on this planet, due to its high rate of rotation and varying gravity, would likely be extreme. The default hoop world of Earth-like conditions is 11 times the surface area of Earth itself. See our episode Megastructures Hoop Worlds for more details.
Hydroshell. A hydroshell is a megastructure designed with the intent of maximizing use of water to generate gravity as one of the most abundant materials in the universe, while simultaneously using it for aquatic living space. A hydroshell is hollow like most shell worlds, but lacks a black hole or neutron star at the center, simply allowing the water itself to generate gravity. As a result, the lowest layer at the shell itself has virtually no gravity, while the top layer has the most, and pressure rises very slowly with depth. Hydroshells can be constructed to produce many thousands of times the normal marine living space as a planet with the same overall mass. See our episode Oceans in Space, Marine Space Habitats for more discussions. See also Shellworlds, Sun Tower.
Interstellar Black Hole Highway. As black holes represent a very good way to accelerate and slingshot spaceships to interstellar speeds, naturally occurring ones may be commonly used as hubs for interstellar travel, including as turning points for ships wishing to save fuel. As such, there may be long lines of traffic moving on lines between the various black holes in our galaxy, forming a highway network. Additionally, black holes make excellent power plants for powering enormous lasers to serve as pushing beams to accelerate or decelerate spaceships.
Interstellar laser highways. Bouncing laser beams off the back of large mirrors allows solar sails to be far smaller and high power than relying on simple sunlight, and may be generated anywhere you can make power. With this in mind, any civilization with fusion or black hole power generation has the option of setting up long relays of laser beaming stations between stars to circumvent the rocket equation and allow rapid and far more economical interstellar transport at a high fraction of light speed, and without the problems of attempting to keep stellar systems or Nitro Dyson beams focused over billions of kilometers or more. This can be a large array of space stations stretching between any two stars or an entire galactic highway system, either receiving pushes from many such arrays between stars or merely as one passes by a star with a beaming system. This technique may also be adapted for intergalactic travel, though it is not thought to be possible to achieve a ship velocity with a Lorentz factor much above 100, where time moves at 100th its normal speed for those on board, as the blue shift of even cosmic microwave background radiation would represent a strong drag force. See our episode Interstellar Highways for more details. See also Interstellar Black Hole Highway, Dyson Beam, and Stellazer.
Jenkins Swarm. A Jenkins Swarm configuration is designed to produce a Dyson Swarm around a star as a wide torus or donut, which might be part of a larger swarm of donuts tilted at different angles. This is believed to allow more stable orbits than the basic Dyson Swarm configuration.
Kalpana 1. Named in honor of astronaut Kampala Chalwa, who died on the Space Shuttle Columbia, Kalpana 1 is a cylinder habitat on the small side of megastructures, taking advantage of the idea that spin gravity to avoid nausea should probably be limited to no more than 2 rotations per minute. Only structures in excess of 250 meters radius can be spun at 2 RPM or less and still produce a full 1g of Earth gravity, so Kalpana is 250 meters in radius and 325 meters long, with roughly half a square kilometer of surface area inside, almost exactly 1/1000th of the surface area of Earth, and thus what we sometimes call a nano-Earth habitat, in contrast to a mega-Earth. However, with a mass of roughly 7 megatons, you would be able to construct roughly 850,000 billion such habitats out of Earth's own mass, 850,000 times the living area, demonstrating the idea that cylinder habitats are vastly more efficient ways to get living area than traditional spherical bodies.
Kipping Terrascope. The terrascope is a concept for taking advantage of the refraction of planetary atmospheres to use them as an enormous lens, allowing a small telescope in orbit of a planet to act as a far more powerful telescope. Developed as a concept by exoplanet astronomer David Kipping in 2019, it is believed it would allow a telescope as small as a meter across to see exoplanets in sufficient detail to detect land masses and mountain ranges. Such telescopes can also serve to enhance signal detection and would also function around larger worlds such as gas giants.
Lagites. Lagites are a variation of statites and normal orbital mechanics, which was suggested by Isaac Arthur in 2016 as a play on the terms lagging satellite and Lagrange point. A lagite uses either light pressure or solar wind on a wide thin satellite to obtain a non-Keplerian orbit by using a combination of inertia, gravity, light pressure, or solar wind to create normally impossible orbit paths, as well as false Lagrange points. As with statites and quasites, this requires a much thinner satellite than normal, but not necessarily as paper-thin as a typical statite. They can be particularly useful for keeping beaming mirrors in position around planets, where the gravity of planet can be used to keep a beaming mirror from floating away into interstellar space. See also quasite, Caplan Thruster, statite.
Lofstrom Loop. A Lofstrom Loop or launch loop proposed by Keith Lofstrom in 1981 utilizes active support to suspend a 2,000 kilometer long runway high in the atmosphere to serve as a launch point for a spaceship. The metal track running inside the loop by active support can also provide the energy to the ship as it accelerates, which in turn is accelerated by power generated by conventional or nuclear power plants on the ground or on naval vessels. A Lofstrom loop may be lowered or raised to avoid bad weather, and it is believed to be constructible with known technology for perhaps as little as $30 billion and a launch cost of just $3,000 per ton. It is a very parallel technology to the larger orbital ring, but does not allow as much acceleration. See our episode Launch Loops for more details. See also Active Support Orbital Ring.
Magmatter. Magmatter is a hypothetical material that may be possible to create if magnetic monopoles exist, and if so, would potentially allow the construction of megastructures whose tensile strength requirements surpassed even graphene, such as Banks orbitals and Niven ring worlds. Magmatter is expected to have a strength a trillion times higher than conventional matter, and a density many trillions of times higher than normal matter. For this reason, we would expect magmatter to be used as infinitely thin structural lines. It is also assumed to have a melting point hotter than the core of the hottest star, and a whipcord of it could cut through any known material, better than a lightsaber. It is usually assumed it would be formed as mag atoms into Bucky tubes, much as with carbon nanotubes. See also carbon nanotubes and graphene.
Matrioshka Brain. A Matrioshka brain represents both a specific structure and the general concept of a computer or computers built to run on the output of an entire star. The Matrioshka portion, named for the famous nested Russian dolls, runs on the idea that successive layers of a stellar engine, each further from the star, can use the radiated waste heat of the prior layer to run more processing on. Stars themselves are not radiating fusion power directly, but rather are incredibly hot from absorbing all the fusion byproducts at the core, and glow as a result, giving off sunlight rather than gamma radiation. One might place processing layers at each halving of temperature, where the next layer is positioned to absorb the black body radiation of the prior layer and re-emit it at a wavelength corresponding to half the temperature of the prior layer, resulting in roughly 10 layers between the typical star's first layer and where the ambient radiation inside a galaxy would result in diminishing returns from additional layers. As colder computation is more efficient and a Matrioshka brain can also act as a stellar engine to move a star, it has been proposed that Matrioshka brains would tend to migrate to the galactic rim or intergalactic space itself. A Matrioshka brain, though, is also a bit of a blanket term for any computer running on star levels of power and can generally be expected to be billions of times more powerful than any modern computer, even if no further improvement in processing per unit of energy occurred in the future. As such, it is believed to be powerful enough to emulate entire universes, and the uploaded minds of the inhabitants of that universe if every single planet was terraformed to current Earth-like conditions and populations. See our episode Megastructures, Matrioshka Brains for more details. See also Dyson Sphere, Planet Brain, Caplan Thruster.
Matrioshka Shellworld. One problem with shellworlds is that they use immense amounts of mass to create gravity compared to cylinder and ring habitats, or those using hypothetical artificial gravity. Two methods for handling this are to generate the gravity with far more abundant materials, such as hydrogen and helium, or even dark matter. The other method is to construct mini nested shellworlds, rising one over the other, to share the mass below for gravity, which can be maintained at the same level by including the mass of each additional layer to generate gravity on the one above it too. Spacing and support may be maintained with Atlas pillars, however you must bring in artificial lighting, and you cannot support many layers before heat dissipation becomes a problem. This is considered to be one of the more probable eventual fates of Earth. See our episode Matrioshka Shellworlds for more discussion. A multi-layered planet can make the lowest level much thicker and space subsequent layers to achieve self-gravity without the central black hole, and is called a super-self. See also active support, Atlas pillars, shellworlds, orbital rings.
McKendry Cylinder. McKendry cylinders, suggested by Tom McKendry in 2000, represent the adaptation of an Island 3 O'Neill cylinder to use graphene instead of steel for the cylinder, allowing for one that is hundreds of times wider and longer. The default version is 5 million square miles, or 13 million square kilometers, as big as Russia or Antarctica, and larger than Europe or Australia, qualifying them as a continent-class megastructure. What's more, a McKendry cylinder is wide enough to allow multiple nested cylinders inside, so long as cooling is used to handle heat issues with artificial lighting, allowing McKendry cylinders to roughly match entire planets in living area.
Megatelescope arrays. One of the limitations on modern telescopes is Earth itself, as air and gravity deform mirrors and limit their size. Space-based telescopes avoid these issues and potentially allow tinfoil-thin mirrors the size of planets to be created, able to see distant worlds in as much detail as current ones can see our own moon or neighboring planets. In addition, telescope arrays may be built in the Oort cloud, allowing thousands of times the distances that Earth's own orbit around the Sun grants us for resolving objects and parallax. Using these methods, we may be able to pick up ETI radio signals even from other galaxies or see exoplanets in great detail thousands of light years away. See our episode Megatelescopes for more details.
Mini-Earth. An alternative to building worlds bigger than Earth is to go smaller. and since the amount of mass needed to produce Earth-like gravity on the surface of a sphere is proportional to the surface area of the sphere, the implied economics for mass would at least seem to indicate that there's no big difference between making one world 1,000 times the size of Earth, 1,000 shell worlds the size of Earth, or 1,000,000 worlds 1,000th the size of Earth. Assuming micro-black holes the mass of a modest moon can be created, it is likely to be easier to make orbital rings which are smaller than a planet, and so small spheres for miniature planets might turn out to be a preference. There are some difficulties making sure your atmosphere stays on such many planets, but a thin glass or transparent aluminum shell around a world would prevent that, and would be easier to engineer than the world itself. As to the minimum size, hypothetically, nothing prevents one smaller than a modest town. These need not be spherical either, as disks or other geometries become more appealing when contrasted to a sphere that is sharply curving.
Mushroom Hab. A mushroom habitat is a concept developed for the episode Colonizing Mercury, where on airless Cythonian worlds blasted by intense sunlight, a large reflective umbrella shade can be placed over a habitat which itself stands above the ground, on top of thermally insulated stilts, resembling a mushroom. This allows the habitat to remain cool even on worlds like Mercury. The umbrella may also be used for power collection. The habitat may also include spin gravity features to allow for higher gravity if the world has lower surface gravity than desired. A mushroom habitat may also be used in orbit of a star to keep a cylinder habitat protected from sunlight, such as a habitat being used for those living on a cylinder habitat who tend solar collectors or stellazers dangerously close to a star. To distinguish between the two types, these are called orbital mushroom habitats. See also Rotor City habitat, parabolic habitat.
Neptunian chainsaw. The importance of scooping gases out of an atmosphere of gas giants, ice giants, or gas dwarfs for use as fuel or for terraforming airless worlds suggests a number of methods for mining them, and one of those is a massive excavator with buckets running on an elliptical orbital ring. This concept is first discussed in our episode, Colonizing Neptune, which, along with its appearance, gets it the name of the Neptunian chainsaw.
Nyko-Dyson beams. The Nyko-Dyson beam is a variant of a classic Dyson Swarm suggested by James Nyko as converting a star into one massive laser platform. There's a number of methods for doing this, including the Stellaser, and it is a capacity of any Dyson that it should be able to direct a large portion of its power into beam weapons, but a Nyko-Dyson beam is essentially a Death Star version, only physically larger. It should be noted that even our sun's entire power output hitting Earth would still take roughly a week to vaporize the entire planet. Those around larger stars might be able to fire beams able to annihilate planets in mere moments. Its peacetime use is soon to be pushing spaceships up to relativistic speeds, though it is likely its military use would be accelerating mini-relativistic kill missiles, or RKMs, to near light speed over some weeks, to arrive in a single moment rather than a beam hitting a planet directly. See also RKMs, Stellaser.
Nova Drive. Nova drives, along with their big brother, the supernova drive, are a method of moving dead stars such as white dwarfs by delivering a stream of hydrogen to them to cause a small nova. This is a parallel technology to the Orion drive, which propels a ship with nuclear bombs, only vastly bigger. See our episode Fleet of Stars for more details.
O'Neill Cylinder. The O'Neill cylinder, originally known as the Island 3 design by Gerard K. O'Neill, is perhaps the most famous megastructure designed for habitation. It is a cylinder habitat usually given as 5 miles or 8 kilometers wide and 20 miles or 32 kilometers long, and this O'Neill cylinder could house hundreds of thousands or serve as a nature preserve for endangered ecosystems, protected by the vacuum of space from invasive species and contamination. They are probably the most discussed megastructure on our show. See our episodes O'Neill Cylinders and Life on Board an O'Neill Cylinder. See also Cylinder Habitat, McKendree Cylinder.
Orbital plates. Orbital plates are a type of megastructure parallel to a sky city that we would anticipate if anti-gravity was invented, where a large domed island might be floated as a spaceport above the landscape, possibly even ones the size of continents, able to float above a world. In practice, this can be achieved through various active support technologies, or through a conventional orbiting habitat that's plate-shaped, using Grav Plating, or the same methods we used for creating disk worlds, if a dense enough material can be found, such as stabilized neutronium. They have appeared in a variety of science fiction over the years, but the name comes from the Warhammer 40k setting, where orbital plates are common around the most important and industrialized worlds.
Orbital Ring. The orbital ring is another technology heavily discussed on this show for its utility both as a space launch option and as the literal backbone of many enormous megastructures, such as Shellworlds. A type of active support structure proposed by Paul Birch, the most basic orbital ring is a simple wire wrapped in orbit in a circle above the equator of a planet. Outside of this is a thin tube, called the sheath, which also circles the planet and contains electromagnets. We then run power through the rings and shove the inner wire up to higher than normal orbital speeds, while slowing the outer sheath. By default, we will stop the sheath when its speed has reached the same rotational rate as Earth, causing the outer sheath to remain stationary relative to Earth, like a geostationary satellite, but potentially mere tens of kilometers above the surface of the world, rather than tens of thousands. Orbital rings may then drop a tether down to Earth, one requiring vastly less strength than a conventional space elevator. They may also be stretched out at angles to service a wide band of Earth's surface around the orbital ring. Using these as guide wires allows the ring to be tilted off the equator to service different latitudes and counter its tendency to precess. This allows travel to space for dollars per kilogram, and the track may then be used like a Lofstrom Loop to launch a spaceship without rocket fuel, only to considerably higher speeds than the Lofstrom Loop allows. Orbital rings may be built as ellipses as well, and a world is likely to have many orbital rings at different distances from Earth, possibly connected to higher rings by tethers to the next lowest ring. They allow hypersonic travel between cities on Earth with minimal cost, potentially allowing millions of people to travel to space every day and home that same night, with normal modern commuting times and costs. They may be used in tandem with space elevators and space towers. Orbital rings of much higher radius can be built in layers with tethers between them to serve as a ladder to deeper space, what we will call an orbital ladder, not to be confused with Jacob's ladder, which along with the orbital tower and beanstalk are order alternate names for space elevator options. The orbital ladder, as an alternative to the classic space elevator of tethers between orbital rings, has the advantage of requiring less tensile strength. These may be built arbitrarily big, and many tipped at different angles can form a spherical shell known as a Shellworld. See our episode Orbital Rings for more discussion of the technology and uses. See also Active Support, Atlas Pillar, Lofstrom Loop, Shellworld, Space Elevator, Space Tower.
Paperclip Maximizer. A paperclip maximizer is a popular example of artificial intelligence run amok. The notion being that an automated paperclip factory, told to maximize its production of paperclips, may seek to cannibalize all available resources, including the planet it is on, and the people on it, into paperclips. This can follow many unexpected paths. See our episode, The Paperclip Maximizer, for more. This popular idea is basically that any automated machinery tasked with a simple goal may run amok if left unchecked. Simple self-replicators told to reproduce themselves are known as gray goo, in reference to an assumed sea of gray metal. Terraforming machinery set loose on a galaxy, turning every world, including inhabited alien worlds, into copies of Earth or entire endless cylinder habitats, is another example, and sometimes called green fly. Given that megastructures are often assumed to need a vast amount of automated constructors, there is a regular concern of such machinery producing one of these scenarios.
Parabolic Hab. The question often arises, how far out can we usefully survive on sunlight? And a parabolic habitat is a method for extending that, and they were designed in tandem with the mushroom habitat concept. Earth typically receives on an order of several hundred watts of power per square meter of surface area throughout the daytime, and any surface colony out near Saturn would need 100 times the sun-gathering surface concentrated to achieve an Earth-like condition. However, as only very thin films are needed for reflecting sunlight, it is not difficult to construct a parabolic dish hundreds of times larger than a given habitat or asteroid to focus light down into that habitat, or into a solar mirror that then bounces light into that habitat. The dish itself is likely to rotate to maintain its shape by spin. Solar power collectors can also be made to function in relatively deep space by using cheap and light-reflecting dishes to focus light on a solar panel or solar thermal generator. By default, we would expect a cylinder habitat with a parabolic dish beyond it, resembling an umbrella or mushroom with a skinny stalk, but it could also be a large dish. Utilizing steadite, lagite, and quasite concepts, this can even be adapted to large self-gravitating bodies such as planets or moons, by using a mix of radiative pressure and orbital mechanics to hang one at a Lagrange point or quasi-Lagrange point. Such mirrors and dishes can also be used for cooling planets or melting icy bodies for transport, including by focusing light on a section of a comet to cause an eruption of superheated steam from it to serve as a rocket engine. See also Helios Drive, Lagite, Mushroom Habitat, Quasite, and Statite for details.
Planet Brain. Planet brains, including examples like a Jupiter brain, are a blanket term for a computer the size of a planet, such as Earth itself in Douglas Adams' Hitchhiker's Guide to the Galaxy. It is assumed such machines either run minds so immense as to be nearly godlike, or seeking answers to the most fundamental questions, such as was the case with Earth in that series, though in that case it was seeking the question, to which the answer was 42.
Planet Ship. Planet ships are artificial worlds designed to serve as immense interstellar or intergalactic colony ships. This is typically intended around an entirely artificial world where a more classic interstellar arc is deemed insufficient to the goals, which might be maintaining civilization and ecology for a multi-million-year intergalactic colonization effort, though similar techniques would be used for moving an existing planet, like Earth, to another solar system. However, artificial worlds such as Shellworld full of fusion or black hole fuel can be built to allow for better acceleration and deceleration for fueling the trip, as well as shielding from interstellar radiation and dust collisions. See our episode Planet Ships and What If Earth Became a Rogue Planet for more details.
Planet Swarm. A planet swarm is a younger brother of a Dyson Swarm, in that it is a large swarm of habitats and megastructures around a planet rather than a star. See Colonizing Cislunar Space for more discussion of the concept. As cislunar space and even beyond the Moon to Earth's Hill sphere is hundreds of times wider than Earth, the cross-section for solar power collection and heat dissipation is more than 100,000 times that of the planet. And thus, while an Ecumenopolis might hold several trillion people, a planet swarm might hold a quintillion. In conjunction with a Terran ring, which it might form the crown stone of, a planet swarm might contain more people than most hypothetical sci-fi galactic empires, and may well be where the majority of humanity lives, even if we have already colonized the entire solar system and thousands of nearer systems. See also Dyson Swarms, Ecumenopolis, and Terran ring.
Planetary Cycler. Also known as an Aldrin Cycler for Buzz Aldrin, who proposed it for an Earth-Mars Cycler, these are large spaceships, stations, or potentially megastructure habitats that move on a very elliptical orbit, passing near two planets on a long cycle. They themselves do not orbit those planets or pause at them, rather smaller vessels dock inside them as they approach that planet or disembark there. As they need only the original fuel to get them into that orbit and some for station keeping, they can afford more massive vessels protection from radiation and can offer superior life support with a multitude of systems of redundancy, and can also offer better living conditions for the long voyages between worlds, or even between stars. See our episode Interstellar Trade and Cyclers for more discussion.
Power beamers. Running an advanced civilization requires immense power, and that may require moving power millions or even billions of kilometers from generator or collector to the user. Power beaming systems can come in many forms, but the default version is likely to be a huge solar array that converts sunlight into microwaves, which can then be transmitted in a tight beam to a retina receiver. Fundamentally, how far you can keep a beam tight is based on the size of the emitter, and the ability to gather a beam as it spreads out, on the size of the receiver. So we may see some truly massive beaming and receiving facilities able to move power across solar systems or even further.
Quasar Drive. The Quasar Drive is a scaled-up black hole drive capable of moving planets or entire galaxies, and it is the ultimate engine for moving large objects, being both faster than a Caplan Thruster to accelerate stellar objects, and more efficient, allowing faster final speeds. The quasar drive takes a charged black hole, artificial or natural, builds a structure around it to attach to it magnetically, and injects matter into it to produce power production as is typical for a large-scale black hole power generator. This is then used to run a drive able to achieve a decent fraction of light speed. The name quasar drive is derived from quasars, the super bright objects which are typically thousands times brighter than entire galaxies, as a result of matter falling into the black holes in the center of many galaxies. Used carefully, a quasar drive on a supermassive black hole in the center of a galaxy can move that galaxy, especially if used in tandem with many other drives throughout that galaxy, gravitationally dragging that galaxy along, which may permit a sufficiently advanced civilization to counteract Hubble expansion in a large region of space, such as a galactic supercluster. Planet ships using quasar drives represent a plausible approach to intergalactic colonization of even galaxies more than 1 billion light-years away. See our episode Fleet of Stars for more discussion of this. See also Planet Ships, Caplan Thruster.
Quasite. A quasite is a variation of a statite suggested by David Kipping in 2019 as a possible technosignature for hunting for extraterrestrial intelligence in the form of a statite that had become dirty or damaged, and thus was orbiting in a non-Keplerian fashion. Quasites can also be intentionally made to create satellites that remain with a planet when not normally permissible by orbital mechanics. See the Cool Worlds episode for more details about statites and quasites. See also lagite, statite.
Red globular clusters. The red globular cluster or red globular galaxy is an example of an artificially optimized galaxy based on the idea that stars of roughly 1/4 our Sun's mass can fuse all of their hydrogen over trillions of years, eventually becoming blue dwarfs, and thus are the most efficient star. The notion developed by Isaac Arthur and Steve Bowers is that a civilization might intentionally work to only allow stars of that mass to form, and may use stellar engineering to crowd them into a tight space so the entire area was bathed in sunlight at a level comfortable for life. A Dyson Swarm composed of as much as 1 trillion such stars might be home to trillions of people for trillions of years, but condensed into a volume only several light-years across, not hundreds of thousands, allowing a single civilization with no more time lag between most distant elements than between near-neighboring stars in a natural galaxy. Even the dying stars themselves, as blue dwarfs cooling trillions of years from now, can be shepherded into black holes of Birch Planets or other post-stellar megastructures. See the original entry at Orion's Arm for more details.
Relativistic Kill Missile. Relativistic kill missiles, or RKMs, weaponize the mass energy of objects moving at relativistic speeds where they might carry hundreds of times more damage potential than a nuclear weapon of the same mass. They have the advantage over beam weapons in that they move at nearly light speed, but can have computers and guidance on board, potentially even AI, and can be slowly charged up. In this way, something like a Nigel Dyson beam, which might need a week to atomize a planet, can instead put a week's worth of energy into accelerating several RKMs, which may be timed to arrive simultaneously and instantly blow up a planet.
Ribbon worlds. Ribbon worlds are variations of ring and cylinder habitats that base their size around the minimum gravity required for their purpose, as opposed to what's comfortable for normal humans and terrestrial ecology, and as such can be far bigger than conventional 1G habitats using the same construction materials. These may be common as an outer ring around planets where they would work as a spaceport and launch systems, and secondary conventional rotating habitats might be attached to them like beads on a bracelet, where those other habitats might serve as the various homes or commercial centers. Ribbon worlds might also be commonly used for space farms, where lower gravity is probably sufficient for plants and economics prefers cheaper and weaker hulls. Civilizations adapted to lower gravity might prefer ribbon worlds as primary habitats. The largest ring habitats would likely always be ribbon worlds. A ribbon world built around the Earth-Moon system out past the Moon's L2 point, where a lunar space elevator might reach, would allow spacecraft to run on the outside of the ribbon at 1G of turning acceleration and launch at 66 kilometers or 41 miles per second. See also cylinder habitat, ring habitat, Space Elevator.
Ring habitat. Ring habitats work on the same principle as cylinder habitats by using centrifugal force to simulate gravity, called spin gravity. A ring habitat, however, generally uses a wide, thin ring, which requires stronger tensile strength than a cylinder habitat of the same surface area, and thus it is assumed to be used where a wider radius is necessary. In the case of small habitats, we expect rings as the living area of many spaceships, where the goal is to produce a relatively small living area with minimal rotation rate, as many RPMs can cause nausea. On large habitats, such as a Niven ring world, the goal is to be far from the Sun at Earth distance, and for a Banks orbital, to produce a wide, skinny ring that is open to natural sunlight. See cylinder habitats for further discussion of how spin gravity works.
Ringworld. The Ringworld first appears in Larry Niven's novel Ringworld as a suggested alternative to a classic Dyson Sphere by taking an equatorial slice of such a sphere around a star and rotate it to produce spin gravity instead. That results in a ring roughly the radius of Earth's orbit around that star. The typical design calls for giant rim walls around the edge to keep the air from spilling out, taller than any mountain range, potentially 1,000 miles tall, but still dwarfed by the width of the Ringworld, which may be arbitrarily wide, but Niven's classic is 1,000,000 miles wide, giving the Ringworld 3 million times the living area of Earth. One built 6 times wider would have roughly 1% of living area imagined by a classic Dyson sphere, and 100 such objects turned at different angles around their star could enclose one to effectively serve as a Dyson sphere. Niven Ringworlds are normally assumed to be constructible only with unobtainium, in the book's case, the virtually indestructible material, Skrith. However, we can get around this for both Ringworlds and Banks orbitals by use of active support. This is done by having a second, slower turning, and far more massive ring just behind the habitation ring in which it spins inside, pushing off the heavier outer ring magnetically to keep from being torn apart. For further explanation of this technique and other Ringworld advantages and challenges, see our episode Ringworlds. See also Dyson Sphere, Ring Habitat, Ringworld.
Rhoda City. A Rhoda City, also called a Bullhab, is typically envisioned as a habitat built inside a crater or artificial well on a low-gravity world and spun to combine the natural local gravity and the spin gravity achieved by rotating the bull shape. In practice, if the gravity of the world or moon in question is not at least half what the desired gravity is, the bull's shape will be much steeper, like an urn, approaching a more classic cylinder habitat. It can also be a wide ring with the floor angled steeply relative to the ground and natural down. These may see use on Mars or even the moon. See also cylinder habitat.
Rungworld. A Rungworld is a cousin to the better-known Ringworld that can be constructed around a star using only conventional materials. In it, we place 2 tethers in a circular orbit around a star, one above the other. Between these, we place classic cylinder habitats so that they appear like rungs on a ladder, the ladder itself being twisted into a circle around a star. These habitats might be O'Neill cylinders or the more gargantuan McKendree cylinders. Much as several Ringworlds, each tilted at a different angle, may enclose a star, many Rungworlds may be built with slightly different angles and diameters to enclose a star. So too, empty space between rungs can be filled with solar panels or ancillary equipment. A topopolis may also be substituted for the tethers between the habitats. Additionally, a Rungworld may skip the appearance of a rung in favor of arranging habitats in a mesh format or even more 3-dimensional formats of a Buckyhab. See also McKendree cylinder, O'Neill cylinder, Ringworld, Topopolis.
Shellworld. Shellworlds are an attempt to save on construction mass by building a thin, rigid shell, akin to the crust of a planet, and filling the middle with a more abundant source of mass, such as hydrogen, helium, or dark matter. Such a shell is usually assumed to be made rigid with either unobtainium or by using active support techniques like orbital rings, though it can be maintained by a mixture of gravity, surface tension, and gas pressure like the Edersphere, which is essentially a big balloon. Most often we imagine millions of orbital rings formed into a spherical shell and covered with a shell and land and sea above, and below a gas giant or even a stellar remnant such as a white dwarf, neutron star, or black hole. In particular, black holes of substellar mass are a popular approach to allowing shell worlds of any given size, bigger or smaller than Earth, but with the same gravity as Earth on the surface. These can vary in size from a modest park to something measured in light years, like the Birch Planet, and additional layers may be built as concentric spherical shells, a Matrioshka Shellworld. See our episode Mega Earths and Shell Worlds for more discussion. See also Active Support, Black Hole Gravity Generator, Birch Planet, Edersphere, Matrioshka Shellworld, Mega Earth, Mini Earth, Orbital Ring, Supramundane World, Unobtainium.
Shikata Thruster. A Shikata Thruster is a type of stellar engine designed for using a star's own power to move it, by surrounding the star in orbital mirrors or statites which reflect light in one direction. With this method, stars can be slowly accelerated up to a small fraction of light speed. Bigger stars accelerate faster as they have a higher brightness to mass ratio, whereas small dwarfs can attain higher ultimate speeds as they burn a larger percentage of their fuel. All versions are slow though, and because of acceleration time, it is a relatively minor difference in effort to move them across a galaxy or even between galaxies, compared to simply moving them a few systems over. See our episode Shikata Thrusters and Fleet of Stars for more discussion.
Sky Cities. Sky cities, or cloud cities, are examples of floating cities that hang in the air via buoyancy or aerodynamic lift, as opposed to anti-gravity approaches such as orbital plates. These might be individual homes, cities, floating space launch facilities like the Dark Sky Station, or even continent-sized affairs on worlds like Venus. Materials able to hold hydrogen or helium better than modern materials, such as graphene, may make these options vastly more economic and safe. By and large, these structures are necessarily big when based on buoyancy. One example is the Cloud9 sphere, which takes advantage of how geodesic shapes grow stronger as they get bigger, to use large, buoyant balloons in buckyball form, essentially a habitat that's shaped like a soccer ball. See our episodes Cloud Cities and Colonizing Venus for more discussion of floating cities. See also Dark Sky Station, Orbital Plates.
Skyhooks. A skyhook, also known as a rotovator, is a long tether that hangs from orbital heights to a lower height for spaceships to connect to in order to save launch fuel. They come in both stationary and rotating form and are a parallel concept to a space elevator, relying on tensile strength. A skyhook loses momentum when giving it to a spaceship as it lifts and speeds it up, but if larger, can slowly regenerate momentum between hookings by options like solar-powered electrodynamic tethering. Skyhooks are a launch assist technology typically designed to be incorporated in tandem with either hypersonic spaceplanes, Lofstrom Loops, or mass drivers. See our episode Skyhooks for more details. See also Lofstrom Loop, Space Elevator.
Smoke ring. In Larry Niven's 1987 novel The Smoke Ring, we encounter a naturally occurring gas cloud surrounding a star in its habitable Goldilocks zone as a wide torus of breathable air with a native ecology. This may also be constructed as a megastructure, in which case it would have a living volume comparable to a Dyson Swarm, and specifically a Jenkins configuration. This concept also arises in Peter Hamilton's Commonwealth saga, where we see entire islands floating through this immense star-encompassing atmosphere, or atmotorus. We could conceive a civilization with either artificial gravity or the capability to manufacture micro-black holes and mini-Earths, filling such a torus with an asteroid belt of such islands whose gravity would keep the air in that torus rather than dispersing to interstellar space. Or we might see a vast, transparent, hollow donut in which the ring was contained. See also Dyson Swarm, Jenkins Swarm.
Solar mirrors. Solar mirrors are a method for directing large amounts of light onto a planet, power collector, or megastructure that take advantage of the incredible thinness of reflective materials compared to thickness of habitation and power megastructures and planets in general. A single micron thick sheet of metal, polished to reflect, like aluminum foil, might double the light coming out of a megastructure habitat at a millionth of the mass of that habitat. In this way, small asteroids, which number in hundreds of thousands, can be converted into a shade able to significantly alter a planet's temperature, such as warming Mars, and indeed a statite Dyson shell around a star would generally require only the mass of a modest-sized moon. solar meals are also instrumental in laser and power beaming technologies for powering worlds or driving spaceships. See also parabolic habitat, solar shades, statite.
Solar shades. Solar shades are a parallel concept to solar mirrors, allowing planets to be cooled or giving them artificially different day lengths, while making use of simple and cheap technology. Any material that can be woven thin allows for shades weighing only a tiny fraction of the typical megastructure, even when of gargantuan size. While these can be employed as a single large shade, it is quite possible that many smaller ones would be used together instead. Additionally, in some cases, it may be considered preferable to use inflated spheres rather than flat sheets, such as filling a L1 Lagrange point with mini balloon shades to bounce around its metastable region, or floating mirror-topped balloons in an upper atmosphere to shade the area below, rather than placing them in orbit or Lagrange points or various statite and lagite orbits. See our episode Winter on Venus for discussion of using solar shades to terraform hot planets. See also lagite, parabolic habitat, solar shades, statite.
Sombrero Planet. This variation of a flat Earth megastructure is an attempt to manage the difficulty of gravity on a disk pointing not just down to the disk but toward the center, by making the disk wider and containing more mass near the end, and by having a bulge near the center. See also Discworld.
Space elevator. Space elevators can be either long tethers hanging from space relying on tensile strength, or huge space towers reaching into orbit, relying on compressive strength. But tensile strength versions are more commonly discussed in modern times, typically expected to be made of carbon nanotubes or graphene. Because a mechanical climber can use electricity on the cable, or beamed power to pull on the cable, cost for ascent to orbit is almost trivial, on an order of dollars per kilogram. A space elevator typically would run to above geostationary orbit, where a ship leaving there would be able to exit at interplanetary speeds, as the elevator's end tip is moving faster than orbital speed at that point. They are most easily built at the equator, but if a material is strong enough, multiple tethers may extend up from the north and south of the equator to meet at a geostationary orbit. A severed elevator tether will see the top spin off into space and the bottom fall to Earth. Though given that virtually all of the tether is in orbit above the atmosphere, a break in the atmosphere would most likely cause a slow, outward spiraling tether that could be reconnected and the lower end to fall to the ground like an electric cable from a tower, possibly slowed by a parachute. See our episode Space Elevators for more discussion. See also carbon nanotubes, graphene, skyhook, space tower.
Space farm. Space farms are a blanket term for any structure principally devoted to agriculture in space, on the grounds that if they have gravity at all, it may be lower and the habitat may be constructed cheaper and thinner, as it is likely to be mostly hydroponics or thin soil full of plants tended by robots. Space farms are an option for worlds such as Ecumenopolis, where landing the food on the planet requires less energy and waste heat than growing it there would. We would also expect them to be an ancillary facility to most space habitats, where food for humans may be grown while leaving the primary hab free for residences and parks. Indeed, these may also be used to supplement local wildlife to allow park and garden interiors of habitats to have a higher wildlife population than the habitat would otherwise support, essentially bird and squirrel feeders. The space farm itself might be attached to a smaller but more sturdily built hab ring for workers or livestock or both. Space farms are likely to be one of the most common, if unglamorous, megastructures. See our episode Space Farming for more discussion. See also Ecumenopolis. Spin gravity. Spin gravity is the nickname for how centrifugal force inside a spinning structure, be it a cylinder habitat or washing machine, simulates gravity for most practical purposes. Typically, the larger the spinning structure in terms of diameter, the better the simulation. Spin gravity relies on the premise that Einstein's assumptions for general relativity are correct, that acceleration and gravity are effectively identical. It is also the reason why people on the space station feel no gravity, as their constant acceleration around Earth is precisely countering the gravity of Earth below. See also cylinder habitat and ring habitat.
Space tower. Space towers, also called space fountains, utilize active support to keep impossibly tall structures erect, those able to rise above an atmosphere and even up to geostationary orbits. Technologically, they function on the same principle as an Atlas pillar, and like the Atlas pillar, one of their greatest values is what they can be used to make, not simply as colossal skyscrapers on their own. Though given that such a space tower might have millions of floors and a square footage equal to an entire continent, a space tower built for habitation can be a world in its own right and home to entire civilizations. See also active support, Atlas pillar, space elevator, Lofstrom Loop.
Stanford Torus. With the possible exception of the O'Neill cylinder, there is no more popular recognizable space habitat than the Stanford Torus, a 10 megaton donut, 1.8 kilometers or 1.1 miles in diameter. This diameter was chosen to be well inside material limits of steel and what is required for Earth-like 1g gravity at 1 rotation per minute. The inner side of the torus is clear to allow light to be reflected in and has a view of the hub, which is connected by spokes to the torus, and the hub is where we would expect ships to dock at. Secondary mirrors around the hub direct sunlight into the habitat to mimic a 24-hour day-night cycle. It was designed as a comfortable home for roughly 10,000 people, though like most habitation megastructures, it is assumed to have a number of additional facilities attached to it, including space farms. See also O'Neill cylinders, space farms.
Star lifting. Star lifting is a technology that seeks to mine the stars themselves by magnetically drawing in elements from the upper regions of a star, often by also stimulating more solar wind, or flares. Our Sun is mostly hydrogen and helium, but contains vastly more heavy elements than all the planets in our solar system combined, with roughly 30,000 Earths worth of metals. Star lifting apparatus is itself a megastructure, but also allows the construction of an entire Dyson Swarm of habitats without needing to disassemble the planets in a star system. It also allows the colonization of stars lacking any planets. Furthermore, it allows the removal of helium from stars to prolong their lifetime, as well as the lowering of stellar mass to extend the star's lifetime or prevent it from going supernova, and forms the backbone of some star-moving technologies such as the Caplan Thruster or Helios Drive. See our episode Star Lifting for more details of the technology, methods, and additional applications. See also Caplan Thruster, Dyson Swarm, Helios Drive.
Statite. Statites are the brainchild of Robert Forward, who suggested the name in 1993 as a mix of static and satellite. A statite is able to hang directly above a star, rather than circling it in a typical orbit. These make use of the radiant pressure of sunlight to allow very thin objects perpendicular to the sun to hover in place by balancing the amount of force the sunlight exerts against the gravity of the sun. A statite must be carefully balanced in terms of its cross-section density so it doesn't float further away or fall closer, and thus would likely include the ability to adjust its cross-section and tilt to allow it to engage in station keeping or even move as a solar sail. The critical factor of statite function is surface or cross-section density, how thick the statite is, and this will generally be on the order of tin foil. As the strength of light and gravity both fall off inverse the square of distance from the sun, a statite of a given surface density functions regardless of its distance from its star. However, it would not function around any star with a different brightness to mass ratio. Statites are far easier to make function around more massive stars, which are far brighter, than they are around less massive dwarf stars, as stars can vary by up to a factor of 100 in mass, but more than 1 billion in brightness for that range. Variations of these can also use magnetics to deflect solar wind ions as an alternative to sunlight or in combination with them. So too, the use of focused sunlight from solar mirrors or beams can be used to allow heavier statites. See also Lagite, Quasite.
Stellar pinwheel. Much as a reflective pinwheel can orbit inside a vacuum, propelled by sunlight bouncing on it, a large solar collector configured as a statite could spin like a pinwheel, driven by light or solar wind or both to generate power. One hanging above the pole of a star could bounce the light back down into that star, causing it to be reabsorbed and re-emitted. Such devices might be used with some versions of star lifting.
Stellazer. The stellar is both a specific concept using enormous mirrors inside a star's corona to create a massive laser, and a blanket term for any enormous laser powered by a star. The stellar is the brainchild of Steve Nixon, who proposed it as a means of using material in a star's corona to serve as a lazy medium. Large, thin, simple mirrors are deployed near a star using spin to keep them rigid and possibly as close to the star as they can be without melting. Light from the stellar body bounces between the two mirrors through the star's thin corona to generate a laser in the normal method. Such a beam can be enormously powerful and possessed of a huge focal range, making it ideal for propelling light cell craft. The term has become a catch-all on the channel for any type of powerful laser running near a star and drawing power off it, including a conventional one using solar panels, but the original concept was discussed in more detail in our episode Colonizing the Sun. Spaceships using stellar propulsion would be able to achieve a high fraction of light speed and could be slowed at their destination by stellars as well, which might be deployed ahead of an arriving colonization fleet, as a solar sail approaching a star and slowing from conventional radiant pressure before entering an orbit and forming the stellar to slow the main fleet, as discussed in our episode Exodus Fleet. As such, they represent a possible keystone of interstellar colonization and trade. Their potential value for terraforming or planetary power supplies is also enormous.
Sun Tower. There are a number of ways we can move large amounts of energy to a planet, and a number of reasons why, but most will generate huge amounts of heat in the atmosphere. A sun tower is one such way of getting around this. If we were seeking to alter a planet's day length by building super towers on a planet above the main atmosphere with reflective mirrors at the top that a light beam could be put on. In this way, like a water wheel, a planet could have a flow of light placed on those towers as it turned to speed or slow planetary rotation. Similar methods can be used to push a planet closer or further from its sun, or to adjust axial tilt. It also is possible to mount a rocket engine, presumably a fusion or ion drive, on top of such towers to avoid atmospheric heating, or to mount magnets against which a beam of particles could be directed. Sun Tower is also used for very tall towers with either a mirror or artificial lighting for keeping a layer of a habitat lit or the surface of a shell world. In some cases, such as a vertical reef for lighting marine habitats, the tower itself might glow its whole length, and it may be covered in fiber optic cables bringing in light from elsewhere. See also Stellar.
Supermundane worlds. Supermundane worlds are a category of spherical megastructures where, typically an existing planet, such as a gas giant, has been wrapped with orbital rings or ribbons or enclosed inside a shell to form an Earth-like planet but one dozens or even hundreds of times bigger. Saturn, for instance, has the right mass and density that if enclosed in a shell just above its atmosphere, it would make for a planet surface 95 times that of Earth but the same surface gravity as Earth. Supermundane worlds can have micro black holes in their centers as well, but are usually assumed to be around gas giants or brown dwarfs, which may be leached to their hydrogen and deuterium to provide power via fusion reactors. Larger ones must be egg-shaped and have their poles wider than their equator to ensure relatively uniform gravity if you're spinning the planet once every 24 hours, so that the centrifugal force at the equator is neutralized by the slightly higher gravity of being above a narrower equator. See our episode Mega Earths for more discussion of the challenge to building such worlds. See also Mega Earth, Mini Earth, Shellworld.
Terran Ring. In terms of fuel, the orbital path of Earth represents the easiest region of space to traverse outside of cislunar space, and thus it is plausible that the ring or torus swept by Earth's orbit of the Sun may be the most densely populated and first developed region of our solar system. It is potentially economically viable to have food production for Earth and its planet swarm in such a ring so that a very dense population could be housed on Earth and in Earth orbit. Indeed, actual tethers could be maintained between habitats and other megastructures in such a ring to allow rapid cable car transport entirely around this torus around the Sun. This may develop alongside or eventually into a rung world. Such cables, if strong enough, could link directly to Earth via various space tower or orbital ring arrangements. See also orbital ring, planet swarm, rung world, space farm, space tower.
Topopolis. Every object, no matter how stiff it seems to us, if long enough compared to its diameter, becomes a flexible rope you can tie in knots, even a solid steel beam as thick as a human, if long enough. The Topopolis takes this a step further and produces one immensely long cylinder habitat that's thousands or even millions of times longer than it is wide, which can wrap around an entire star, or in theory, between 2 stars or even a whole galaxy. In this way, the Topopolis can potentially rival Dyson Swarms or even Birch Planets and Supercell for living area and require no advanced technology. By default, a Topopolis can be pictured as a long skinny cylinder with a river running down it, and the local areas wrapped around it potentially stretching billions of kilometers. The width might be comparable to an O'Neill cylinder or a McKendree cylinder, or whatever your technology permits. See our Topopolis episode for more details and various subtypes of this structure. See also Birch Planet, Dyson Swarm, McKendree cylinder, O'Neill cylinder.
Unobtainium. Unobtainium is a common term for any material in theoretical scientific or sci-fi discussion with properties viewed as fantastic or unobtainable inside modern known science. This might be a stable transuranic element or a material of unbelievable strength, or possessed of a property we would not expect to find in nature, like absorbing neutrinos to emit gravitons. See also Clarketech.
Valley House. Valley houses are where very large craters on airless or low-gravity thin-aired worlds are glassed over to create a habitable area parallel to domed cities. To be megastructures, these would cover valleys parallel or larger than Earth's Grand Canyon or Noctis Labyrinthus on Mars.
World House. A world house is where para-terraforming of domes on a planet such as Mars have encompassed the entire world inside a massive greenhouse, or perhaps even a single crystal sphere has been placed around it to keep an atmosphere in. This may be an early state of a planet during classic terraforming, or it may be a permanent arrangement for low-gravity or lower escape velocity moons and mini-Earths, where maintaining an open atmosphere might be difficult.
Wormhole. Wormholes are a hypothetical object for circumventing the speed of light that would likely be a vital megastructure if they are possible to build. Wormholes and wormhole networks represent a possible Clarketech solution to interstellar travel that would supersede interstellar black hole highways, though likely still be in use with interstellar laser highways for intersystem traffic. See our episode Wormholes in our Fast and Light series for more discussion, and that series for more discussion of how civilizations might incorporate technologies such as wormholes, warp drives, hyperspace, and other hypothetical FTL methods. So this episode obviously ran longer than any other we've had, and was quite a lot of work. And I want to thank my wife Sarah for helping on the narration, and all the editors who helped on the script cleanup, as it ran over 18,000 words, to ensure that there was a proper transcript and subtitles on the episode, something the original did not have, though every episode since has. Another thing that the original did not have, and we introduced a few episodes in, is a credit roll at the end, something that's a bit of a rarity on YouTube for some reason. I wanted to mention that because over the years we've had over 100 folks contribute to editing or animating, or letting us use their music or even composing songs for the show, and we always put those folks in the credits to give them some well-deserved recognition and thanks. Amusingly, today is the first time we've ever had a co-narrator on an episode that wasn't a collab episode with another show. We've even had a dozen or so co-written episodes before today, and yet weirdly, for a show where the host has a big speech impediment, no other narrator. Anyway, I want to thank all those folks who've contributed over the years to this episode and to the 470 other entries on our big chronology spreadsheet, which includes over 100 bonus episodes and live streams and collabs. I know the production number on the show says episode 346, but I only count the regular Thursday episodes towards those, as they're really more like production week numbering these days. I also want to say a big thank you to the National Space Society for hosting me at their International Development Conference last week. I'd been set to attend 2 years back and collect my Pioneer Award for them, but then COVID came, and so 2 years later I finally got to give a talk there, and revisiting that original topic of megastructures seemed a good topic, and that evolved into this episode. You can catch the recording of that talk too, as it was substituted in for our normal monthly livestream Q&A. So too, a lot of that first episode's original content was inspired by the collection of futuristic ideas and structures at Orion's Arm, and it's been a great source of futuristic content for a couple of decades now, with both visual and text entries on many topics in their Encyclopedia Galactica, but also with many stories written by its members dealing with life in the future and often on such megastructures. Alright, that wraps us up for today, but not for this week, as we have our Sci-Fi Sunday episode, The Silurian Hypothesis, coming up this Sunday, June 12th. This is the concept that some ancient civilization like intelligent dinosaurs might have once dwelt on Earth long ago. We will also ask what would remain of humanity's accomplishments millions of years from now if we suddenly died off. And 2 weeks from now, we'll be looking at the concept of interstellar probes, where we will begin our two-part story of traveling to an anomalous system to investigate it, concluding with life as a planetary explorer. We will pause between those two episodes to look at the concept of colonizing the galaxy, how humanity can still settle the stars even if we are limited to spaceships moving at less than 1% of light speed, and what that will look like. One more thanks, and that's to all of our donors over the years. You've made the show possible, whether it was on Patreon or by PayPal, or Subscribestar or Snail Mail or Nebula, and I am beyond grateful. This show would not exist without your support. For anyone who would like to help support future episodes, you can go to our website, isaacarthur.net, which we recently relaunched new and improved, and all those other options are linked in the episode description, along with our social media forums like Facebook, Reddit, and Discord, where you can chat with others about today's episode and many other futuristic ideas. And thanks to all the admins and moderators on those forums for their hard work too. And don't forget to like this episode and subscribe to the channel and leave a comment below. As always, thanks for watching and have a great week.